Hello, my wonderful students. I welcome you all to today's lesson. And today we are going to be treating the topic reflection of light by curved mirrors. By the end of this lesson, the student should be able to, number one, distinguish between the two types of curved mirrors. Number two, draw ray diagrams to show the formation of images by curved mirrors. Number three, use the mirror formula to solve some problems relating to curved mirrors. And number four, mention some practical applications of curved mirrors. Now, let's look at the topic properly. There are two types of curved mirrors. Number one, we have the concave mirror, which is otherwise called the converging mirror, and the second one is the convex mirror, that is also called the diverging mirror. How can we distinguish between these two? A concave mirror is just a portion of a hollow sphere that the outer surface is painted with silver, or the outer surface is opaque, meaning that light cannot pass through it, and it makes a parallel beam of light to converge at a point. So whenever you pick a convex mirror or a converging mirror, you will notice that the reflecting surface curves inwards, while the opaque surface, or the surface that is painted with silver, curves outwards. What about the convex mirror? A convex mirror is also a portion of a hollow sphere, but the inner surface is painted silver, or is opaque. And this type of mirror makes a parallel beam of light to appear to diverge from a point. So in this type of mirror, you will notice that the outer surface, which is the reflecting surface, curves outwards, while the side, or the surface that is painted with silver or that is opaque, curves inwards. Okay, we have a typical diagram there to illustrate a concave mirror, and the first diagram we have there, if you look at your screen, you will see the concave mirror. You can see there that the reflecting surface, and also see the opaque surface. And you can see that if you complete that semicircle there, which forms the mirror, you will notice that the outer surface is the side that was painted silver. Now, if you check the second diagram, which is for convex mirror, you will also see that the curved mirror there, the reflecting surface curves outwards, while the other one, which is the silver surface, you can see that is now inwards. Okay, that's that for the two types of mirror. The next heading now we have is the definitions of terms on these curved mirrors. The first term we are going to define is the pole. If you go back to the diagram we had there, you can see where we have points labeled P, the other point we have F, and we also have C. Then between P and C, you can see a small letter R there. Those are the things we are going to be defining. You can also see the line that is drawn from the pole there, and that is labeled the principal axis. So we are going to look at all these terms and define them accordingly. P there stands for pole, F stands for the principal focus, C stands for the center of curvature, and the small letter R there stands for the radius of curvature. What is the pole of a mirror? The pole is the center of the reflecting surface of the mirror. So if you check the diagram, you can see that the pole is just the center of the reflecting surface of the mirror, The second term there is the center of curvature, labeled C. What is the center of curvature? We have that this is the center of the sphere of which the mirror forms a part. The center of the sphere of which the mirror forms a part. The third term there is the radius of curvature. That's our small letter r, and we have that it is the distance between the pole and the center of the curvature. So we have their distance PC, P there for pole and C there for center of curvature, and it can also be defined as the radius of the sphere of which the mirror forms a part. The fourth term there we are going to look at is the principal axis, and we have that the principal axis is just the line PC, that is the line drawn from the pole to the center of curvature. The next term there is the principal focus, capital F, and we have that the principal focus of a curved mirror is the point on the principal axis where all rays close and parallel to the principal axis converge or appear to diverge from after reflection. The point on the principal axis where all rays close and parallel to the principal axis converge or appear to diverge from. Okay, we have a diagram here to illustrate the principal focus of a concave mirror and also that of a convex mirror. Let's look at that diagram critically. You can see the first diagram for the concave mirror. You can see incident rays there, parallel rays, and you can see them moving and they strike the mirror, and once they strike the concave mirror, what happens? They will be reflected backwards, and all these rays will now meet at a point. That point in which they will now meet is the principal focus of that particular mirror. Okay, for the second diagram we have a convex mirror there. We also have incident parallel rays. You can see what happens in the second diagram there. These rays now strike the convex mirror. What happens? These rays, they now all diverge. Instead of converging, they now diverge. Now you can see what happened there. If we recall what we did in convergent beam, we now assume and say if these rays, we trace them backwards, that is at the back of that mirror, they will now meet at a point. That point in which they will now meet is the principal focus of the convex mirror. Note that this principal focus is a virtual focus. That means it is not real. Remember, we have distinguished between two types of images, the real image and the virtual image. So for this principal focus for convex mirror is a virtual focus. It's not real because we just assume that if we produce these divergent beams or rays and produce them backward, they will now meet at a point. So it looks as if they are coming from a point F. Looks as if those rays are coming from this point F. So that's a virtual focus. But for the first one, which is the concave mirror, the principal focus there is what? A real focus, because you can see that the rays actually converge at a point. Okay, now let's look at the last term we are supposed to define there, which is the focal length, represented by the small letter F. What is the focal length of a curved mirror? And we have that this is the distance from the principal focus to the pole, and it is equal to half the radius of curvature. If you go down to the diagram we had before, you can see the principal focus there and the pole. Okay, You can see the principal focus and the pole, and we have that the focal length is the distance between these 2 points. And if we recall, the distance from P to F is equal to the distance from F to C. And also remember that C to P is equal to our radius of curvature. So if F to P is equal to a small letter f, which is the focal length, it then means that our focal length is equal to the radius of curvature divided by 2. Okay. Now, having learned the parameters of a curved mirror, we now look at the formation of images by curved mirrors. Okay. Now, what you have on the screen there, we have that the nature, position, and the size of an image formed by a curved mirror depends on 1, the position of the object from the pole of the mirror. That is the factor that the nature, position, and the size of an image formed by a curved mirror depends on. That is the distance of the object from the pole of the mirror. So from this hint we have below, we will now be forming our images, taking note that the position, nature, and the size of the image that we form will now depend on the where the object is placed. You can see from the diagrams we have previously, we have 3 cardinal points on a principal axis. What are those 3 cardinal points? The center of curvature, the principal focus F, and the pole. So we are going to be forming our images by placing objects at these different points, maybe at a distance beyond C, then at the distance C, then at distance between C and F, then at the distance F, then at the distance between F and P. From these different points, we will be forming different images. Okay. Now we have the hints, or we say hints, that we have to note before we can form our images appropriately. So let's look at those hints. Okay, if we look at those hints, the first hint we have there is that a ray from an object that is parallel to the principal axis will pass through the principal focus after reflection from the mirror. That's the first hint we have to note. So if you have a ray and the ray is from an object and that ray is parallel to the principal axis, after reflection, that ray will pass through the principal focus. And the second hint there, a ray from an object that passes through the center of curvature will reflect back through the same line. So we have the second hint there. If you have a ray and that ray passes through the center of curvature, which is our capital letter C, once that ray passes through C, that same ray will also reflect back through the same C. Okay. Now the point of intersection of these 2 rays, will give us the top of the image form, or indicates the top of the image formed. Okay, so with hint 1 and hint 2 we can comfortably form our image, but we can also have the third hint there and use it. And the third hint says that a ray from an object which passes through the principal focus will emerge parallel to the principal axis after reflection. I take that again. A ray from an object which passes through the principal focus will emerge parallel to the principal axis. Okay, that's the third hint and the final hint there. If you look at the third hint there, you see that this hint has a kind of similarity with the first hint. For the first hint, ray that is parallel to the principal axis will pass through the principal focus. Then the third hint, a ray that passes through the principal focus will now emerge parallel to the principal axis. So they are just the opposite of each other, or we say the reciprocal of each other. So we can also call on the third hint to form our image. Okay, now let's use these 3 hints to start our work. Now, first of all, we will start with concave mirror. The first one, object placed beyond C. The image formed is real, inverted, diminished, and located between F and C. That's the first one. If you place an object beyond C, the image that is formed will be what? Real, inverted, diminished, and located between C and F. Later we'll look at the diagrams for this first one, but let's take the second one and the other ones before we now cross-check them in the diagrams we have. And the second one, object placed at C, the image formed is real, inverted, the same size as the object, and located at C. Okay? The next one is object placed between C and F. The image formed is real, inverted, magnified, and beyond C. The fourth one, object placed at F. The image formed is real, inverted, magnified, and at infinity. And the fifth one, object placed between P and F. The image formed is virtual, erect, magnified, and behind the mirror. You can see the fifth one, the image formed is now virtual. That means there is a condition for a concave mirror to form a virtual image, and that condition is when the object is placed between P and F, a virtual and erect image is formed. Remember that a concave mirror usually forms what? A real image. But under one condition, this concave mirror forms a virtual image. And that is when you place the object between P and F. Okay? Now, let's look at diagrams to illustrate these 5 positions that we have placed the object. You can see A there. A, remember that the A stands for object placed beyond C. You can see the object there standing at a point X. Can you see that? Okay, I'll use that first one to recall what we have mentioned for the hints we used in forming this image. Okay, let's check at that. Let's check that object. Please look closely. You will see that there is a ray from the top of this object, and that ray is parallel to the principal axis. Parallel to the principal axis. I hope we are seeing the principal axis there. The line drawn from P to C. Okay, that ray now is parallel, and remember that hint 1 said that ray after reflection will pass through the principal focus. I hope you can see that the ray now passing through the principal focus. Now the second ray, what happened to the second ray? The second ray passes through C. Can you see that? If you look at that, you will see the second ray passes through C and it is reflected back through the same C. Check that. You will see a ray passing, striking the mirror at a point E, and is reflected backwards through the same point. Now, ignoring the third line, the third one, remember the third one, from the diagram there, they use the 3 hints. You can see the third hint there. The third ray passes through F. As you can see, it passes through F and strikes the mirror at a point D. And what happens to the third hint? A ray that passes through the principal focus will emerge parallel. You can see it emerging parallel to the principal axis. All these 3 rays will meet at a point, and that point in which they will now meet is indicating the top of the image formed. Can you see that? You can see the image formed there labeled I. So that image, what are the characteristics of that image formed? We have that the image is, number 1, real. Why is it real? Remember that we said that a real image is an image that can be cut on a screen. That is when we are doing it practically. But theoretically, a real image is an image that is formed by the actual intersection of light rays. You can see there is an actual intersection of rays there, so that image is real. Can you see that? The second characteristic of that image is that it is inverted. So you can see that that image is upside down, so it is inverted. And the third one, it is diminished, meaning that it's no longer the same size as that of the object. It has reduced in size. And finally we see that image is located between C and F. Okay, that's for the first one. Let's go to the second one. The second diagram is for the second position, which is object placed at F. You can see that, object placed at C. You can see the object is now placed at C. What happened? A ray passes from the object, strikes the mirror. That ray is parallel to the principal axis, strikes the mirror, and passes through what? The principal focus, F. The second ray, what happened? You can see the object is already at C, so we cannot use the second hint now, because the second hint say a ray from a ray that passes through the center of curvature, but the object is already at the center of curvature, so we leave the second hint, go to the third hint. What happens to the third hint? A ray that passes through F. You can see the ray now passing from the object and passes through F, strikes the mirror at D, and it emerges parallel to the principal axis. And when that happens, you will see there is an intersection between ray 1 and ray 2, and that point of intersection gives us the top of the image formed. What are the properties of this, or the characteristics of this image form? 1, it is real. 2, it is inverted. 3, it is same size as the object. And 4, it is located at C also. We can see that the image is also at C. And that is the principle behind the working of what? The photocopying machine. You place the material you want to photocopy at the center of curvature of the photocopier, and you get exact copy of what you want to photocopy. So that's the principle behind the working of a photocopying machine. Okay, we take the third diagram there. The third diagram now, we are going closer. The object is now placed between C and F. I hope we can see that. Object is placed between C and F. The first ray strikes the mirror at B and is reflected through F. The second ray passes through C and reflects back through the same C, and there is an intersection. And an image is formed, and that image is magnified. So characteristics: the image is real. There is an actual intersection of rays, so it is real. 2, it is inverted, as we can see. And 3, it is what? Magnified. And we can see that the position is now beyond C. Okay? Now let's look at the fourth one. The fourth one, now we move closer again and place this object at what? The principal focus of that mirror. And if we place the object at the principal focus of that mirror, what do we have there? We can see that the object is now exactly at F. So the first ray passes from the object, strikes the mirror at B, and is reflected backwards through F. The second ray passes through C and is reflected back through the same C. Now, what do we have there? You can see that the first ray and the second ray are parallel to each other. I hope we can see that the first ray and the second ray are parallel to each other. So if you keep on moving the two rays, they will keep on being parallel. And the question is, can two parallel lines meet? Can two parallel lines meet? Yes, in physics, two parallel lines will meet at infinity. I know it sounds somehow, but in physics, two parallel lines will meet at infinity. If you have been doing fine art, I think fine art, they say the two parallel lines meet at the vanishing point, which is also the infinity. So the two parallel lines will meet at infinity. Now, because the two lines or the two rays will meet at infinity, that means once they can meet, that means the image formed is real. One, and because it is real, it is inverted. Every real image must be what? Inverted, or is inverted. Okay, so because it is real, it is inverted, and we can also accept that that image is also magnified and at infinity. Okay, we'll take the last one, and that is the only condition for a concave mirror to form a virtual image. I want us to look at that one critically. If you look at that diagram, you can see that the object is now placed between F and P. The object is placed between F and P. Now, let's follow the hint once more. The first ray passes from the object, hits the mirror at a point B, and is reflected through F. That's hint one. The second hint, the ray passes from the object and passes through C. And what happened? It is reflected back through the same C. You can see that these two rays, unlike the one placed at F, which are parallel to each other, these two rays are not parallel to each other. They look as if they are inclined at an angle. So what do? We recall what we have done in what? Divergent beam. What do? We say these two rays that are like this, if we keep on producing them backwards, they will now meet at a point, and that is what happened in that diagram. So we keep on producing the two rays backwards, and the two rays will now meet behind the mirror. And once that is done, the image form is virtual, and you can see the virtuality of the image being indicated with what? Dotted lines, and the rays outside the reflecting surface of the mirror also being indicated with what? Dotted lines. So you can see the characteristics of that image form. 1, the image is virtual. 2, it is erect. And 3, it is magnified. You can see that it's magnified. That means it is what? Larger than what? The object. And finally, it is behind the mirror. That's all for concave mirror. What about the convex mirror? Okay, what we have here is that for the convex mirror, the image form is always virtual, erect, diminished, and behind the mirror, no matter where you place the object. Okay, I take that again. For a convex mirror, the image form is virtual, erect, diminished, and located behind the mirror, no matter where the object is placed. So with one diagram, we can just explain that, because no matter where you place the object, you still get the same thing. Unlike that of a concave mirror, where when you place at different distances from the pole of the mirror, you get different characteristics of images formed. Okay. Now, there is one thing we have to note here. You can see that a concave mirror can form a virtual image under one condition: when the object is placed between the principal focus and the pole of the mirror. But a convex mirror forms a virtual image no matter where you place the object. But the question now becomes, how do we distinguish between a virtual image formed by what? A concave mirror and that formed by a convex mirror? And there is only one difference between them. The one formed by a concave mirror is magnified, while the one formed by what? A convex mirror is diminished. Let's look at that diagram to understand what we have there. Okay, you can see the object is placed already in front of the convex mirror. What happens? We'll take the ray from the object, strikes the mirror, and what happens? Because it's a convex mirror, that ray diverges. You can see it diverging upwards here. The second one, a ray passes from the object and is now, it passes from the object, crosses the mirror, although that is a virtuality being indicated there. It crosses the mirror now, and we now assume that it has also crossed the center of curvature, and once it crosses the center of curvature, it will also go back through the same center of curvature. Now, because the first ray diverges, we now call on the principle of divergent beam and say, since this ray is moving this way, if we produce it backward, it will meet at a point, and that point will be our principal focus. So you can see the ray now being produced backwards, and you can see where this ray now intersects with the ray that passes through the center of curvature, and where the two of them intersect forms the top of the image formed. And you can see what happens there, that the image form is what? Diminished. It is virtual, it is erect, and it is behind the mirror. Okay, that's all for formation of images by what? Curved mirrors. Okay, the next heading we will take is mirror formula. We are going to just a little bit summarize the mirror formula here. Mathematically, the mirror formula is expressed by the equation 1 over u plus 1 over v. Sorry, that should have been 1 over u plus 1 over v is equal to 1 over f. Take note of that. 1 over u plus 1 over v is equal to 1 over f, where u represents the object distance, v represents the image distance, and f represents the focal length. Okay, we in your textbook, if you consult your textbook, different ones, the New School Physics or any other one, you can see that we have two ways we can use this mirror formula to solve mathematically. Either you use the new Cartesian or you use the real is positive. But what I'm going to introduce here now will take care of them. We'll take care of the two methods. In as much as you follow what I'm going to explain here now, you will get the answer very, very correct. Okay, I take that for a concave mirror, V and F are positive. Note that for a concave mirror, the image distance and the focal length are positive, but the image distance V is negative if a vectoral image is formed by the mirror. Remember that I have said that, or we have seen that this mirror can also form a vectoral image when you place the object between the principal focus and the pole of the mirror. Remember that. So when this happens and a vectoral image is formed, V takes a negative sign. But for a convex mirror, both V and F are negative. Okay, so with this small hint I've given, there is no question you will be given or you will be asked to solve that you will not get the answer correctly. Okay, we have under that if we plot a graph of 1 over u against 1 over v, the intercept on either axis is equal to the reciprocal of the focal length. So we have a diagram there. There is a graph there. Plotting a graph of 1 over u against 1 over v, you can see that that is what? An inverse graph, and the intercept at A is 1 over f, and the intercept at B also is equal to 1 over f. Let's take some examples to digest what we have done so far. Okay, the example number 1 there, an object is placed 20 cm in front of a concave mirror of radius of curvature 30 cm. Calculate the position and the nature of image formed. Okay, solution to that question, the first thing we have there is if we are writing out our parameters, we have the first one is object placed 20 cm. That means our u is 20 cm and r, radius of curvature, is 30 cm, and we are looking for position of image form, that is our v. The nature, when they say the nature, they want you to tell them whether the image form is real or it is vectoral. Okay, since we have noted that our focal length is also equal to the radius of curvature divided by 2, we can now get our focal length, and we have that f is equal to 30 over 2, and that is 15 cm. Using our mirror formula, we have 1 over u plus 1 over v is equal to 1 over f. If we substitute or make our 1 over v the subject formula, since we are looking for v, we will now have that 1 over v is equal to 1 over f minus 1 over u. Substituting 1 over 15 minus 1 over 20 is equal to 1 over v. Okay, hence we have that our 1 over v now becomes, if we find the LCM of 15 and 20, that will give us, okay, they use 300 there. You can also use 60. Okay, we can also use 60, but since we have 300 there as the LCM of 15 and 20, then we have that 15 into 300 gives us 20, and 20 into 300 gives us 15. So we have 20 minus 15 all over 300, and that gives us 5 over 300. Therefore, the value of the image distance becomes 300 over 5. Remember that 1 over v is equal to 5 over 300. Therefore, you cross multiply to have your V, and that will give us 300 over 5. And 300 over 5 is what? 60 centimeters. That means that the image distance is 60 centimeters. And you can see real was written beside it to show that it's real. How do we know that it's real? Because the answer we have gotten is what? Positive. Once your answer is positive, that image is real. But if the answer is negative, the image is virtual. Second example, okay, an object is placed 15 cm in front of a convex mirror and an image is produced 5 cm behind the mirror. Calculate the focal length of the mirror. Okay, that's another simple one. The first parameter we have there is our u, and our u is 15. Okay, and the next thing there is our v, which is 5 centimeters. U is 15 centimeters, V is 5 centimeters, and we are looking for our focal length. I want us to take note of something. The first example we had there, we should be able to note that was for concave mirror. So whenever you are given a question, the first thing you ask yourself is this mirror a concave or a convex mirror? Okay, because we have already discussed the criteria for you to solve. If it is a convex, both V and F are what? Negative. But if it is a concave, V and what? F are what? Positive. But V can also be negative if the image form is virtual. So let's look at that second question example again. You can see that it's what? Convex mirror. That means V and F should be negative. Okay, let's look at the solution again. So we have our mirror formula already there. So let's substitute from our mirror formula 1 over U plus 1 over V is equal to 1 over F. Okay, so we have 1 over 15 minus 1 over 5. Okay, why do we have minus there? Because V is negative. Because V is negative. So if 5 is minus, that minus 5 will affect our plus sign there in the mirror formula equation, and you have minus. That's why we have 1 over 15 minus 1 over 5 is equal to 1 over F. Someone will ask, why didn't we put minus 1 over F there? The reason we didn't put minus there is because, please take note of that, because that's the only way to solve effectively. The reason we didn't put minus because we are already looking for F. Since we are looking for F, don't bother putting minus sign there. When you finish solving, the answer will come out to be what? Minus. Okay. Now, if we do our LCM again, we will now have that the LCM of 15 and 5 is 15. 15 into 15, 1, and 5 into 15, 3. So we have that 1 over F is equal to 1 minus 3 all over 15. And 1 minus 3 is minus 2. So we have 1 over F is equal to minus 2 over 15. Therefore, if we cross multiply, our F becomes minus 15 over 2. And that gives us minus 7.5 centimeters. You can see that the answer has come out to be minus. Okay, so take note of that. If you are looking for V or F, that means they were not given and you are looking, they ask you to calculate any of them. Leave them to be plus at that moment. When you finish solving, the answer will come out to be minus. We'll take the final example there, number 3. A concave mirror of radius of curvature 20 centimeters produces an inverted image 3 times the size of an object. Calculate the object's position. I love this question. This is an application question, and we have to apply very, very well. Okay, let's look at parameters we have there. The first parameter is our radius of curvature, which is 20 cm, and if radius of curvature is 20 centimeters, it means that our focal length is 10 cm. That is 20 divided by 2. Then the next thing we have is magnification. Because of that word 3 times, that means magnification. We have done magnification in our pinhole camera. Recall that magnification is what? Image distance all over object distance. So that magnification is 3. If it is 3, it means that our V now becomes 3U. Do the mathematics, it's very good and very simple. So what we are supposed to have there is that 3 is equal to V over U. Therefore, V is equal to 3U. Now, using our mirror formula once again, we have 1 over U plus 1 over V is equal to 1 over F. Let's look at the summation there. Okay, we have 1 over u because we are looking for object position. That is our u. So we have 1 over u plus 1 all over 3u. It is not minus because we are dealing with a concave mirror. If it is a convex mirror, that will take a minus sign. Or if we were told that an erect image is formed, please take note of that. If the question says it produces an erect image, once you see erect image, that image is virtual. But if it is inverted, it is real. So when they say an erect image, so you have to make v to be minus. Okay, take note of that. Okay, so we have 1 over u plus 1 over 3u is equals to 1 over 10. LCM of that, there we have that LCM of u and 3u is 3u, and u into 3u is 3, and 3u into 3u is 1. So we have 3 plus 1 all over 3u is equal to 1 over 10. If we do the mathematics well, you can see that we are supposed to have 4 over 3u is equal to 1 all over 10. And if you cross multiply, you will be having 4 times 10 is equal to 3u. Therefore, u is equals to 40 over 3. And the final answer to that question is that the object distance is 13.3 centimeters. Okay. Now, let's look at the next thing we have there. The practical applications of curved mirrors. Okay, that's the last site heading for this topic. Okay, the first one we have there is concave mirrors are used as shaving mirror, dentist mirror. Second one, also concave mirrors are used as reflectors in reflecting telescopes and microscopes. The next one we have is C for convex mirrors. Convex mirrors are used as 1. Supermarket security mirrors, II. Driving mirrors of motor cars. Now, pay attention to this question. You can, if you check your past wire question, you see they normally ask this question. The 2 advantages of using convex mirrors as driving mirrors, and maybe 2 disadvantages of using them also. That's what we are going to take now. The advantages of using convex mirror as driving mirror. Number 1, they give erect image of an object. Take note of that. It might not be the same way on your screen, but the first advantage of using convex mirror for driving is because it gives an erect image. If you use concave mirror gives what? An inverted image. So there will be a lot of confusion when you are driving with that. So it's not possible. But for a convex mirror, they give what? An erect image. And the second one, they provide a wide field of view. These are the 2 advantages of using convex mirrors as driving mirrors. 1, they give erect images of objects, and 2, they provide wide field of view. You can imagine that small mirror beside the driver there. The driver will be able to see a large portion of area behind him. Okay, what about the disadvantages of using this for driving? We have also some disadvantages of using convex mirror in driving. 1, the image is smaller than the object. Remember that from the formation of images that we have done, you can see that the image formed by convex mirrors are always what? Diminished. So that's a disadvantage. The image is smaller than the object, and the second disadvantage is that it gives a false impression. It gives a false impression of the distance. False impression of the distance as image seems further away. So that's what you notice, especially when you are inside the car. You will notice that the image that you are seeing there seems further away from where the object is actually. Okay. Another type of mirror is the parabolic mirror. It's also a curved mirror from the word parabolic, and this is a special type of concave mirror which has a shape of parabola, and it produces a wide parallel beam of light of constant intensity. Produces a wide parallel beam of light of constant intensity when a small light source is placed at its principal focus. And what are the uses of these parabolic mirrors? They are used in car headlamps and searchlights. So if you look at the diagram there, you can see there is a light source that is being placed at the principal focus of this parabolic mirror. And what happens? The light source now will, at a different direction, strike toward the parabolic mirror, and all these rays we are able to move in what? One direction, parallel to each other. So we can apply this in our searchlights and also car headlamps. Okay, we have been able to exhaust what we have for today. We are going to stop for today till we meet in our next class. But before I leave you, you have an assignment there. You are going to do this assignment and submit accordingly. Number one question there is: a concave mirror of radius of curvature 20 cm has a pin placed at 15 cm from its pole. What will be the magnification of the image formed? And number two, explain with the aid of diagrams how a concave mirror could be used to ignite a piece of carbon paper, produce an exact copy of a picture on a screen. That second question is a site-wide question. So we are going to stop here for now till we meet in our next class. Please remember to always stay safe. Thank you.